Hello everyone, welcome back to the channel. I am Vikash and on this channel we are explore the engineering behind apps we use every day. Today we are going to answer a question that most of us probably never thought through. How does a Uber finds your driver in just few seconds? Think about what just happened. You tapped a single button, waited for a couple of seconds, and suddenly a driver was assigned to you. It feels so simple that we rarely stop and think about what's happening behind the scenes. But imagine this. At this very moment, there could be thousands of drivers moving around your city. Every one of them is changing location every few seconds. Some are available, some are already on another trip, some are heading toward heavy traffic. Yet somehow the app finds one suitable driver almost instantly. Here's the interesting part. The app doesn't check every driver in the city. If it did, every booking would become slower and slower as the number of drivers increased. So, how does it do it? In today's video, we are not just going to answer that question. We are going to think like software engineers, build the solution step by step, and even implement the core idea in Java. So, let's get started. Alright, let's forget about Uber for a moment. Imagine you are one of the engineers building a brand new ride booking application. Your manager comes to your desk and gives just one requirement: find nearest driver. That's it. Seems pretty simple, right? Let's say a customer requested a ride from this location, and around them there are several cabs. Please excuse my drawing. Now, our job is to choose the best one. So, here's a question for you. How would you solve this problem? If this were a coding interview, what would be your first approach? Don't worry about writing the perfect code. Just think logically. How would you find the nearest driver? There isn't much information available. We only know where the customer is and where each driver is. One obvious idea is calculate the distance from the customer to each available driver. Once we have calculated the distance, simply choose the smallest one. Now honestly, this is not a bad solution at all. In fact, if you answered this, congratulations, your solution is correct. Many people think engineering is about finding clever solutions immediately, but it's not. Great engineering often starts with simple solution and then improve. But now let's make this problem more realistic. Instead of 5 drivers, imagine we have 50,000 drivers or even 1 million. Just imagine these are all drivers who are currently available around the customer who is searching or who is raising for the booking request, and this number could be 50,000 or 1 million. Would our solution still work? That's where software engineering becomes interesting. A solution that works isn't always a solution that scales. So, before we write a single line of Java code, let's see what happens when our simple idea meets millions of users. Now, let's test our solution. Earlier, we had only 5 drivers. Checking every driver wasn't a problem. But now, imagine a real city. Thousands of drivers are moving every second. New ride requests are arriving continuously. Drivers are accepting rides, completing rides, and changing their locations all the time. So, here's the question. Every time someone book a ride, are we really going to check every single driver in the city? Imagine 1 million drivers, one booking request, 1 million distance calculations. Now imagine 10,000 people booking ride at the exactly same time. That 10 billion distance calculations for just one moment in time. Notice something. We are actually repeating the same work again and again and again. Even though most of all the drivers are nowhere close to the real customer. So, does that really make sense? So, in this solution, the complexity of this solution is simply order of n. Now, in this type of solution, the amount of work increases as the number of driver increases for each and every request. So, for request 1, the same 1 million distance calculation request to another 1 million, and if we increase the number of drivers, the work will also get increased. Twice the number of drivers, so twice the work. And that's exactly the problem. Now let's stop thinking like a programmer for a moment and start thinking like an engineer. Let's say I live here in Mumbai, and if I book a ride, should it make any sense to check a driver who is 50 kilometers away? Of course not, right? Then why are we searching the entire city? This is the moment where engineering changes, not because we found a faster algorithm, not because bought a bigger server, because we ask a better question. Instead of asking how can we search faster, we should ask why are we searching all of this? And once we ask that question, complete different solution starts to appear. So instead of searching the entire city, what if we could search only a tiny part of it? Now let's see how. Imagine dividing the entire city into smaller regions, almost like drawing a giant grid over a map. Now, instead of treating the city as one huge surface, we have divided it into hundreds of much smaller surfaces. Suppose our customer is standing here. Earlier, we were searching through the entire city, checking every driver in the city. But now, let's first identify that which grid the customer is available. Suddenly, our search space becomes much smaller. So, instead of searching the entire city, now we will search through this grid only. Now, cell may contain 20 or 25 drivers or even less. From 50,000 drivers, we have improved our search to 25 drivers, and that's already a huge improvement. And we haven't written a better algorithm yet. We have simply stopped doing unnecessary work. But what if there isn't enough good drivers in this cell? Now that's a good question. So we will simply expand our search. First we check this cell. If we don't find the good drivers, we will expand our search to its neighboring cells. And again we can level up one more cell further if needed. So notice something here. We are still not searching through the entire city. We are only expanding as per our need. This is how software engineers often solve large-scale problems. Instead of making the search faster, they make the problem smaller. That's a very different way of thinking. And honestly, this idea appears everywhere. Google Maps, food delivery, nearby restaurant, delivery partners, even game. Whenever you need to find nearby object, reducing the search space is usually the first step. So, if there is one lesson that I want you to remember from this video is to reduce the search space first and then optimize the solution. Now our problem has changed completely. We no longer have 50,000 drivers. We only have a handful. So here's our next challenge. Out of these nearby drivers, how do we choose the best one? That's where our data structure finally enters in the picture. So far, we have solved the first problem. We are no longer searching the entire city. We only search nearby drivers. But another question remains. Which driver should we assign? The nearest one? Not always. Imagine one driver is physically closer but stuck in the traffic, and another driver is slightly further away but on an empty road. Which one should we choose? The customer doesn't care about the shortest distance. They care about who reaches them first. So choose the minimum ETA. That means we should choose this drive. So how are we going to choose now? So suppose these are our nearby drivers. Each driver has its own estimated arrival time. Now our goal is simple. Find the driver with the smallest arrival time. One way is to check each and every driver one by one. Now that solution will definitely work. But software engineers usually ask, can we organize this data better? This is where priority queue becomes useful. Think of this as a collection that always keeps the highest priority item at the top. In our case, highest priority means the smallest ETA. So whenever we will ask who is the best driver, the answer is immediately available driver at the top. So in the priority queue, the driver B will be at the top, then driver D, then we will have C, driver A, and finally our data structure will have driver E inside this priority queue. Let's say while we are searching for the best driver, the driver B has already accepted a different ride. So what we will do, we will basically remove driver B from the queue and driver D will automatically become the next best candidate in the priority queue. So no need to search the entire list once again. The priority queue always keeps the next best option ready for us, and that's exactly why it's used in so many real world systems. Now notice what happened. We didn't start with priority queue. We first starts with entire city, then we reduced our search area, and then we search for the best available driver, and then we used the priority queue. So that's an important engineering lesson. A great data structure cannot fix a badly designed search. Now let's put everything together. So start with entire city. Now reduce it to nearby region. Next find available driver. Then based on their ETA we will create the data structure and finally find the best option. So the entire problem suddenly feels much easier. Now we have spent almost entire video understanding the problem. Now, writing the solution will surprisingly easy. Let's build step by step. We are not trying to build the entire backend of the ride booking application. We are only implementing the code matching idea. So let's start now. To keep the driver's information, we will use a driver class. So let me define the driver class. I am keeping everything simpler here. Okay, I am not making it unnecessarily complicated. So inside the driver class, we will have ID to identify each driver uniquely. Then to get the location of the driver, we will have latitude and longitude of the driver. Finally, we will have the ETA time for the driver. That's it. We have kept it very simple. And we will use the existing class from Java collection framework, the priority queue. So which will always keep our priority, the highest priority data at the top, right? In our case, highest priority means shortest ETA. So priority queue of driver class, right? Let's say nearby drivers. Okay, which will have nothing but equals to new priority queue. Now in order to compare between all the candidates and keep the highest priority at the top, it needs a comparator, and we will pass a comparator inside the constructor. Okay, and comparator, what it will compare? It will compare the int ETA in our case. So we will use comparing int driver dot ETA. That's it. That's how we have defined our collection to keep the nearby drivers. And to add, whenever we find a nearby driver, we will add that driver into this collection. So to add this, we will use the offer method of the queue. Okay, so nearby drivers dot offer, let's say driver 1, and similarly driver 2, and so on. To get the selected or the best available driver, we can use the poll method. Okay, so selected driver is equals to nearby drivers dot poll. That's it. So you must have noticed something. Our Java code is actually very small. That's because the difficult part was never writing the code. The difficult part was designing the solution. Good software engineering is like that only. Once the design is ready, the implementation becomes much easier. In just few lines of code, we have implemented the matching logic. Now, I would like to remind you once again, this isn't a production write booking backend, but it captures the same engineering thought process. Reduce the search space, organize the remaining data efficiently, and then select the best candidate. But here's something more interesting for you. Real ride booking applications don't stop here. They consider more things. They will always consider then they will consider driver's rating, surge pricing, and much more. So let's take a quick look at how real-world systems go beyond our simplified model. So, have we built a complete ride booking system? Not even close. What we have built today is the core engineering idea. And honestly, that's the hardest part. Once you understand how to think about the problem, you can gradually make the solution smarter. Real ride-hailing platform consider many more factors. Is the driver currently available? Is there heavy traffic on the route? Is the road temporarily closed? How accurate is the estimated arrival time? Should the driver receive another ride request? Or are they about to finish their shift? The modern system even uses machine learning to predict the ETA more accurately. The engineering becomes much more sophisticated. But if you look closely, everything still starts with the same engineering principle. First, reduce the search space, then organize the remaining data efficiently, and finally choose the best candidate. That's exactly the journey we followed today. So, the next time you open a ride booking app and tap book ride, you will probably get a driver within few seconds. But now you will know that behind those few seconds, thousands of engineering decisions are working together to make that simple experience possible. And that's exactly why I love software engineering. The most beautiful solutions are often the ones users never even notice. They simply press a button and everything just works. If you enjoyed this breakdown of the engineering behind a ride booking app, don't forget to like the video and subscribe to the channel. And I would love to hear from you, which app should I reverse engineer next? Let me know in the comment below. Until then, keep learning, keep building. I will see you in the next video.